chapter 4 is all about atomic structure. So we're going to start off with looking at the early atomic models. So one of the first people to influence this thought was a guy by the name of Democritus, and he was a Greek philosopher, and he suggested the idea of the atom as the basic unit of matter. And the word atom comes from the Greek word atomos, and that means indivisibly. And so that basically meant that the atom was the smallest piece of matter and that it couldn't be broken down into anything smaller. His approach to the atom was very philosophical. Rather than experimental and scientific. So an atom is the smallest particle of an element that retains the property of that element. So late in the 1700s, we began working on the atomic theory. The definition by this time of the word element was widely accepted, and it was clear that elements combine to form compounds. Both of these were very accepted in the scientific community. However, there was some disagreement about whether elements combine in exactly the same ratio when they form compounds. So in 1790s, there was a greater emphasis on quantitative analysis of chemical reactions. And quantitative analysis really focuses on numerical data. And so with that, they came up with the law of conservation of mass. And that says that during a chemical reaction, the total mass of the products must be equal to the total mass of the reactants. So this also brought about the law of definite proportions. And this says a given chemical compound always contains the same elements in exactly the same proportion by mass. So, for example, water contains 11.19% hydrogen and 88.89% oxygen. So, how did they figure that out? And so, when you look at the chemical formula for water, we have the formula H2O, so that means we have 2 hydrogens and 1 oxygen. And so when you look at the periodic table, the mass of hydrogen is 1.0079, and the mass of oxygen is 15.99. And when you multiply those through, you get 2.0158 AMUs, or units, for the mass of hydrogen, and then the 15.999 for the mass of oxygen, which brings the total mass of a water molecule to 18.0148. And so then to figure out by percentage, you take the mass of hydrogen, the 2 atoms of hydrogen, over the total mass of the compound, and you would multiply that by 100, and you end up getting 11.19% of that compound is hydrogen. And then you repeat that process for the mass of oxygen, so 15.999 over the total mass of the compound times by 100, and you'll get 88.81% is oxygen in the compound water. So we can try another one. Calculate how much carbon by percent is in carbon dioxide. So the first step is to find the total mass of the compound. And that's going to require you to know and use the periodic table. So we have 1 atom of carbon, and the mass of carbon from the periodic table is 12.011, for a total of 12.011. Then we have 2 oxygen atoms, and oxygen is 15.999. And since we have 2 of them, that multiplies out to 31.998. So to find the total mass, you add those 2 numbers together, and when you do that, you get 44.009. And so since it's just asking for how much carbon by percent, we only have to worry about putting the 12.011 in the numerator over the total mass of the compound times 100, and you get 27.29% of that compound is carbon. So, sticking with the 1790s, we also get this law of multiple proportions. And this states that whenever the same 2 elements form more than one compound, the different masses of one element that combine with the same mass of the other element in the ratio of the smallest whole number. So what this is basically saying that if, let's say we have carbon monoxide and carbon dioxide, and so since they both contain the same elements, but they're combining to form different ratios, that in a given mass of carbon needs to combine with exactly twice as much oxygen to produce CO2 as it does to produce CO. So we keep 1 gram of carbon, since there's only 1 carbon in each of these. And then when we look at the oxygen, we need exactly twice as much. So in this particular, we have 1.33 grams of oxygen. And so in carbon dioxide, when we have 2 oxygen atoms, we need exactly twice as much mass of oxygen in order to make CO2. So this is all a great start. And in 1808, an English chemist and a school teacher by the name of John Dalton based an atomic theory off the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So his law said that all matter is composed of atoms, and so that he got from Democritus. And he also said that atoms of the same element are identical when it comes to size, mass, and other properties. Atoms of different elements can chemically combine in simple whole number ratios to form compounds. And chemical reactions can be described as either separation, combination, or rearrangement of atoms. And so Dalton's theory was widely accepted, But there are some flaws to it, which we'll talk about later.